Okay, so off to chapter 2, which is actually the most recent unit we've been working on, dealing with polynomials, factoring, roots, graphing, and rational equations. Mixed emotions. Sometimes I don't review this one since it's so fresh, so new. A lot of people kind of feel comfortable already and they don't really need to spend a lot of time on it since we literally just finished it. But on the off chance that there's some places where you're struggling with that, we'll go ahead and look at that anyway. So in the very first question that we have, we were looking at the possible rational roots. So the word rational just means there's a fraction involved or a problem that can be written as a fraction. So Descartes figured out that all you had to do is take a look at the last piece of a polynomial right here, this minus 26, and take a look at all of the numbers that divide perfectly into that number minus 26, and then also look at the first number, which is the 2 right here, and look for the numbers that divide evenly into the 2. And so, in other words, I see that we could have numbers like 1, 2, 13, and 26 as numerators and 1 and 2 as denominators. That leads us to a series of fractions, and you'll notice that I didn't write every fraction out there. Like I didn't write 2 halves and I didn't write 26 halves because those were already included in my list. And since this is supposed to be a list of potential answers, then we kind of can stop fairly quickly. So given this crazy polynomial that I have above right here in number 1, for problem number 2, we just said, hey, so let's suppose that I happen to know that 2 minus 3i is a root, and I want to find the rest of those. Now, that sounds like it's going to be a lot because this is a 4th degree polynomial, so there should be a total of 4 roots if you're going to find all of them. But when I told you that 2 minus 3i is a root, then by default, we also know that 2 plus 3i has to be a root as well. So we had a couple of ways that we could do that. One of the tricks that we learned is that if 2 minus 3i and 2 plus 3i are roots, then we have this special trick that we could add those together. And notice when you add these 2 roots together, the i's cancel and we get a 4. And the rule was subtract that. So if it was a positive, we get a negative. If it was negative, we get a positive. And also, we just square each of those coefficients, the 2 and the negative 3. Well, 2 squared is 4, and negative 3 squared is 9. 4 and 9 make 13. And so as it turns out, we could do long division on this 2x to the 4th, 11x cubed, all of this stuff. And we will get the same answer as we would if we did the synthetic division. Now, every year I have a matter of people that like one, people that like the other. But if we had 2x squared, that would make 2x to the 4th. We could have a negative 8x to the 3rd plus 26x squared. We could change our signs and add down. Now, the thing that we are guaranteed in this particular problem is that when we're all done, the remainder is going to be 0. So I kind of got it started, but I'm going to go ahead and finish it in the other way. So what I chose to do instead, just to kind of show the other possibility, is if I knew that 2 minus 3i is a root, then I just took 2 minus 3i, and I is that second decimal. I stored that as a. And so I can then use my calculator to do this work. So we drop the 2 down. And if I multiply 2 by a, that goes right there. I subtracted 11, and I got negative 7 minus 6i. I multiplied by a to get the number right here. Add 36. I've got it. Multiply by a again. That's going to give me 35 plus 6i minus 31. So you notice I'm using my calculator to do all this heavy lifting times a, and if we have done right, we're going to get the number 26, and it canceled out. Now, the nice thing is we've already divided this out, but we have terrible looking coefficients. We had a 4th degree, and now we have a 3rd degree with imaginary values, which we don't want. But if we have this problem, we can use its conjugate. And notice when you drop the 2 and you multiply, the I part goes away. You multiply again, the I part goes away again. And so I end up with this simple little quadratic, and we're actually pretty versed at solving quadratics. We know how to factor them, so I had 2x squared to get this. Negative 2 has to be a 2 and a 1. Play with your pluses and minuses, and that's what we got. So I know that 2 minus 3i, 2 plus 3i, positive 2, and negative 1/2 are in fact every possible root of this particular polynomial. Okay, so moving on to number 3. Now number 3 is one thing that we really haven't done a whole lot of. This is a rational inequality. Again, so when we look at this problem, I know there's a lot of things happening here. I know that I would get 0 at 5/2, and 0 is actually a good number. 0 is fine to get in a numerator. I know that negative 1/3 is fine to get in a numerator as well. But negative 4, which is way out here, is not okay because that would be division by 0, and that's the one thing you're not allowed to do. So to finish that problem up, then what I want to do is just try a value. So pick a number to the right of 5/2, like 10 or something like that. If you picked a 10, you'd get a positive here because 31 is positive. 20 minus 5, picking 10, was a positive, and that's positive. So clearly a positive times a positive over a positive is positive, but I don't want that. I only want numbers that are below 0. And it turns out I really don't have to work very hard because none of these terms are squared. So trust me on this, if you went and you tried 0, you're going to get a negative in here, which is actually something we want. If we try a region in here like negative 2, it's going to be positive and then negative. So if we're wanting negative values, then we're happy with this part and this part and those parts only, which leads me to the answer that I have right here. So for number 3, I set it up like I had, and then I wanted to cherry pick the values between negative infinity and negative 4, where I'm desiring negatives, and also the numbers from negative 1/3 to 5/2. And notice that I cannot have negative 4 because that would be division by 0, but I can have these because this actually asks for negatives or 0. Now, problem number 4 is a little bit trickier. So in that particular problem, I believe it was asking us to find every possible asymptote. And so since we have a 3rd degree divided by a 2nd degree, this should be a 1st degree or a slanted asymptote. And there's pretty good potential that I'm going to have a couple of verticals. So I did go ahead and factor that. So I have a 3rd degree divided by a 2nd degree. I factored and I saw the 2 vertical asymptotes at 6 and at negative 2. Now, you could have chosen to divide by x squared minus 4x minus 12 using long division, but you guys know me, I really like synthetic a lot. So I set up the problem noticing the 0 because the x term that was missing. I did synthetic division on on 6, excuse me. You can see the process here. Remember, we don't bother to look at that remainder because in synthetic division, when we're looking for asymptotes, we throw it away. And then when I was done with that, then I divided negative 2, and there is my slant asymptote. And keep in mind, you can always double check those. And again, I don't have this set up, so I'm modeling how long it takes to do. So if we had 4x to the 3rd, minus 18x squared plus 5, and I wanted to divide that by, and I believe in the original problem it was not phrased this way, so I'm just going to go back to x squared minus 4x minus 12, simple little equation, and I'm going to go ahead and graph that together with that slant asymptote I found 4x minus 2. I don't know what the right window is to do, but I'm guessing sometimes they get kind of big, but I bet this is going to be good enough. So here comes my equation. Oh, something weird here. I don't like what I see. I must have missed a parentheses. I've got 4x cubed minus, well, let's see. Maybe I didn't give myself enough window. must be missing some parentheses in here. Let's see. So I had 4x cubed minus 18x squared plus 5. Oh, I missed my parentheses. Over that one, that shows you how important that is. So I'm going to go back to that previous window because I really didn't want to make something quite so obnoxiously large. Boy, parentheses can get you. And so here comes my original graph. It's got some asymptotes, which no big surprise there. And here comes my slanted asymptote, and it kicks through quite nicely. You can see that it seems like it matches not on the side, on the middle, but it does quite well on the sides. Now, for question number 5, I wanted to make, and number 6, I wanted to kind of create my own functions that did something kind of special. So in number 5, if I wanted to have a vertical asymptote at -2/5 and at 2, then I pretty much had to have a 0 on the bottom at -2/5 and -2, because that's going to make one vertical at -2/5 and one at 2. Now, the interesting thing here is it says I want a horizontal at -6. And we only got horizontal asymptotes when the powers of the numerator and denominator were either the same or the bottom was bigger. But since it's a number, I want them to be the same. So since the power of the bottom is like a 5x squared, I needed the top to be -30x squared to make that -6 happen. Now, the reason I said plus anything is it could be +0, +1, +6, +18, you know, pretty much anything I want, as long as I didn't accidentally pick a factor that would cancel this out and make it removable. Now, for problem 6, we again wanted a removable discontinuity at -3/5. Well, automatically a removable means we need common factors. So I had 5x plus 3 over 5x plus 3. That common factor is going to make a removable discontinuity. I want let's see, a vertical asymptote at 1/2. That's going to put something in the bottom right here, 2x minus 1. And last but not least, a horizontal asymptote at 3. So again, like this one, we need to have matching powers. So since the bottom is a 10x squared, the top needs to be 30x squared. So again, there's a lot of variability on what I could put over here. It could be a 0 or a -1 or an 85. It doesn't matter, but no matter what, that's going to work. So I did give you a couple of options of like what I could have done. You know, it might have just been 6x, which is what I see most frequently. Some other people go 6x minus 5 or some such. It's not that big of a deal. Now, for the last one for this particular video is number 7, is we're going to write one more equation that has root at -2. Now, as soon as it says it has a root at -2, that's very different. This is the exact opposite of what I was saying up here. Because up here, if you have a vertical asymptote at -2/5, that's what you can't have. But if you have a root, then you can have it. So I'm going to put an x plus 2 in the numerator because I wanted a root that's going to make it happen. Now, next, we also want to have a root at 0. Well, that immediately shows me that I'm going to want to have something. Let's see, let me double check that. Oh, it has 2 vertical asymptotes, one at -2/3. That's going to be 3x plus 2. And another one at 0. That's going to be an x. And here's the last one. It said that somehow, as I go to infinity, the graph is going to go down. So that means somehow I need to come up with something where the numerator is bigger than the denominator. So I just picked a -2x squared because now I'd have a -x cubed on top and I'd have an x squared on the bottom. Now I put -x cubed. It's really 2x cubed, but it doesn't really matter. As long as I have an x cubed, this is going to divide out to leave a -x, which is going to make that problem go down towards infinity. So that's the first 7 problems on that unit review, and I think that should be sufficient for the time being. That was pretty long, so hopefully it wasn't too hard. Bye-bye.